All right, welcome to part 3 of my quad tree implementation in SIG series. And this time I'm gonna go through a couple of optimizations that we could do. They're fairly quick to do and gives, somewhat of an improvement at least. So let me bring up my notes here. Yeah, so the first thing that I want to do is instead of having optimization. So instead of having this add page here, if we look at this function, we are calling resize on entries for each page. We're calling resize of pages. And resize actually goes in and calls ensure total capacity, which also does a bunch of stuff. It grows the capacity. It calls ensure total capacity precise, which might also so it resizes the memory location or the allocated memory, and it might keep it at the same location, but it also might move it to a new location. And since this is like I was gonna say this is an easy way to implement this, but we know that since we know all the pages that's required, or we don't know all the pages actually, but we know the number of entries at least that we have for the population. So in that case, when you're only using the quad tree as a static quad tree, you can actually do an optimization here, which you prepare all pages beforehand. So you do like a one resize for all the entries that you would need, and you do one resize for all the pages that you would need. So you don't have to do this a lot of times over and over. And the way I'm doing it here is that I have I'm gonna define a function that is called prepare to add pages, and I'm gonna take in pointer to qt. I'm gonna have number of pages to add, or number of pages, and in here first we need to calculate how many pages do we actually need to add. So I'm going to say that this is pages to prepare is going to be number of pages minus the min value of number of pages and self.available pages. So we're going to have a function called available pages, which returns how many pages do we have left to be able to like allocate, let's say. How many pages do we have in our array list that's not been used yet, basically. And so if we want to prepare more pages, then we can count those off here. Well, yeah, this is just to make sure that if we call prepare add to pages again, yeah, I think I don't really need this right now. If you're only gonna call this once, then we don't really need it. I did it in another way before, but yeah, let's just do it like this. And let's say that, yeah, so we do the resize in here instead. So we do pages resize. And how many pages do we need? Well, we've got the pages that we have available is going to be Oh yeah, then we use the current page index. So I've actually written it like this: pages items length plus pages to prepare, but it's like the number of pages. So we'll just do this, and then we have entries. We also resize the entries. And here we need to times this by max entries in page. So this function, if we send in one, that was gonna prepare one more page basically. If we need more pages, then yeah, which we are going to need, it's gonna we can pass that in, and that will resize these entries as it needs to. And so well, basically from the start it's just going to be like the pages length is going to be 0, but then we'll resize it to how many pages that we need. And so in our insert or populate function, after reset we can do prepare to add pages. And how many pages do we need? Well, I've been counting, and it's not enough to just say entries length over max entries, because the reason is, well, it's not a division issue, but the reason is that you might have quadrants, and in the case of quadrants you might have pages that are not fully utilized. You might end up with a lot more pages, or a little bit more pages than you need basically in order to store these. But it's just based on how this works basically. Like we populate all the quadrants, even though we might not need to have the quadrants, but we do it just because it's simple that way. And so what we do want to do is, well, we have this division, so we could do that. And then we can say we need to do, I think, 4 times this, because yeah, because of the quadrants. So this is not exact either, but it seems to work good for what we need. So yeah, it's better to overkill this than to not, because what happens is the page list or the entries list is going to relocate to another memory location, which invalidates all pointers that we currently have to those places, which breaks some of this this quad tree. And that's a bug that needs to be fixed if it's going to be a dynamic quad tree, but now it's a static quad tree, so it's enough to just allocate as much as we need from the start and populate everything from there. So then, so yeah, so we do prepare to add pages, and then instead of add page, we do add page prepared. I'm just gonna rename it, because we're not gonna have an add page method yet. So what this is doing, it's not gonna resize anything. It's not gonna resize that. Yeah, I need to catch unreachable here as well. So it's gonna just assume that we have the space. So yeah, it's gonna, we could add asserts in here. So we could assert that the, yeah, that the number of pages, I think it's pages items length minus current page index. This is the number of pages that we have currently available. That should be more than equal to 1 when we do add page prepared. However, I'm not gonna assert that right now. I'm just gonna trust that this will work. And yeah, so we have our entry slice and everything here. Yeah, so that should be good. And that is actually all we basically need to do to make this work, actually. Yeah. So in our insert, we call insert into page, and we call we call subdivide. Yeah, subdivide. This one also calls add page prepared. So this should up the FPS by some amount. 344. Oops, we got some issues here. Okay, index out of bounds at 208. Okay, so I missed something here. So it has length 40. Wait, 40. Where did I put this prepares thing here? So we got entries items length plus max entries in page times number of pages. And it's going to be 4 times entries length over. Yes. Oh, yeah. We need +1 as well because of this truncation which is going on here. But it's still, I mean, it's 4 times, so yeah. Let's do this. Okay. Will that fix it? It feels like it shouldn't fix it, but it did. Okay. Okay, we got about 370 FPS. And what if we revert these changes? We can go back. So yeah, I think that's enough. We revert it, and yeah, there's basically no difference. Okay. I mean, it should be a little bit of difference, but maybe it's not that much of a difference because we are adding well, we are doing resize on both things. Yes, I thought there was going to be a lot more difference on that actually, but maybe because it's not that many entries. Yeah. Let's do this. And also I lost all the changes, but I'm just gonna do this real quick here. So prepare to add pages, number of pages, and resize. Entries, results, number of pages times max, catch, and show. All right, we remove these, remove that, and we go up to populate, and we do self.prepare, and number of pages going to be 4 times entries length over max, and +1. There. Let's just see if that works. Yes. Okay. Now I'm going to go to my debug scene here. I'm going to add 300 bodies instead. See how that looks. Yeah, it's struggling. Yeah, It can't really go all the way up to 300 bodies. Otherwise, it would have filled the entire screen, because that's how my populate function is doing it. So if we wait, oh yeah, I am doing the optimized way to do it. Why is it so slow? I mean, when I test this earlier with the other implementation that I did first, I actually got way better performance. I could add like 1,000 bodies without any issues. Maybe it's the low. It's shouldn't be that much of a difference. Maybe. Oh yeah, it is. Okay. Yeah, the log is like spamming into the. It takes a while to write it, but okay. We get 200 FPS in this method, and let's see. Let's add some more bodies. Let's do like 1,000. Should be able to do that, hopefully. And you can see FPS is going down, and it's going down, and there we go. So we have 1,002 bodies at 58 FPS. And let's see how it does if we don't prepare. We can actually do a prepare here instead. So we call prepare, and this is basically equivalent to what we did before. We call these once per add page. So this would probably be a lot slower, not a lot slower, but no, maybe not. Oh, there we go. We got some issues here as well. I think we reached a point where, well, it's slower and it also is susceptible to this. I think, yeah, this is because of we got a segmentation fault. So we access some memory that we shouldn't. And it's probably because of the array list relocating to another place where it gets more room, and then a bunch of pointers gets invalidated, and we're not updating that properly. So because we are relocating and doing that, we get invalid pointers, and then we're trying to use those pointers and it crashes. So yeah, that's one other issue with this. I'm not gonna fix that right now, but we can see that we actually get some improvement. Performance is what I was trying to say. Performance improvements by doing this premature, or not premature, but like, yeah, we do this beforehand in a bulk, so to speak, operation. Resizing the things, and then we add all the things. So that works a lot better, and it avoids the relocation issue as well. I also saw before that we do get a lot of entries that basically not gets not part of the tree, basically. And that causes, I guess, maybe causes some issues with the collision. I mean, it should cause issues with the collision. You can see here that I'm able to move a little square around. It's kind of hard to see which one I'm moving, but it's right now sort of in the middle, the one that's floating around in different directions. Everything else is basically set on a frictionless right now path to well, whatever is hitting it, it's gonna change its direction and stuff, and velocity. Yeah, so I've not implemented friction in the physics engine yet, but yeah, This is more to showcase the quad tree anyway. So, but yeah, so you can see here the quad tree is faster. It works without relocating and crashing. There's one more optimization that I want to do, and it's the one that I talked about in the beginning of the last video. It's here. So we do this one now for the global collision phase. We do for each body call intersect on quad tree. So we are first building the quad tree, and then we go through each body and we call intersect on that. So what I want to do instead is, while building the body, I want to check for intersections for each insert, basically. So so the idea is that you don't have to do as many checks as you would need otherwise, because you're checking each call to the intersection will have to check against everything else. But if you do it one by one, or after you just inserted something, then you don't really need to check a lot of or you cut down on the number of checks that you need to do, basically. And you can basically only do this if you're doing it like in this kind of static quad tree thing, where you build the quad tree and then you build the quad tree each frame from everything, and then you rebuild it every frame. Yeah. So so I want to make another function called populate and intersect. I think I called it. Looking at my other notes in here. Yeah. So populate and intersect. And this is gonna take in the quad tree, is gonna take in boundary, entries, and then it's also gonna take in a callback. And usually in Zig, the way you do callbacks is, first you have a context, which can be anything, and then you have the function. And then you're gonna call the callback, which we're gonna call intersection handler, with the context as the first argument. So it's basically like a self type function. Well, it could be, it doesn't have to be, but so you put the context there as a type of context, and then you have what entry is colliding, and then you have the list of intersections that the entry is yeah, colliding with. And then yeah, so that's our intersection handler. And then we do the same thing. We do reset, and then we also do a prepare to add pages. So we do basically do the same thing. Difference is that down here, when after we've inserted body, we need to check the intersections. So we get the intersections like this. So self intersecting. And then we need the AABB for the entry. So we can do this. There. Now we got the intersections, and then we can just call the intersection handler with the context, the entry, and the intersections. So, and that's basically all you need to do for that. And yeah, and this should hopefully, if I'm not mistaken, I very well could be, but this should work the same way, at least for well, it should produce the same collisions, I hope, basically. So, but what I need to do now is wire up this in my collision container. Well, not the collision container, in my physics system. I have these two different approaches, and I need to replace my previous approach where we populate and then we do go through each body and check for collision. So now what we do instead is we call a we call from collision container. I have another function called check collisions qt, which does the thing that we're talking about. So I commented out this because we didn't have this function before, and yeah, it's just yeah, we have a collisions buffer, which is it resets here, and then you have the tree populate and intersect function, which we're just calling from the quad tree directly. So and here we pass in boundary, we pass in all the bodies here, we pass in the context, which is self, which is my collision container, and then the handler, which is defined down here like this. And this takes the collision container, the body that is collide or intersecting with another body, or this list of intersections we get here, and we go through the intersections, and we yeah, basically do the same thing as we're doing otherwise. So yeah, it is basically returning or it's making like a list of collisions, and then it calls like a yeah, it basically populates this collisions list, and then we use it in the. We haven't gone through this code, so I'm not gonna explain more of this. But yeah, so now it's all wired up, and let's see if we get some. I guess if we could see if we got some better FPS from that. I'm not sure. I think what I saw is it gives about 10 FPS or something like that. It's like 5-10 FPS difference. So it's not really that much of a difference actually. So I thought it was gonna be more of a difference, to be honest. But yeah, it's not really a lot of difference here. I mean, if we look at it, an example here. So if I have my little cube up in the top left corner here, and or rectangle, I should say, and yeah, it's if we think about what's actually being checked here, it's gonna be this blue. I'm not sure if you can, yeah. This blue square here, this quadrant, and all of these largest quadrants are being checked first. This is going to be checked first, and if this returns, if this is checked first, so this is gonna return true for the. Actually, let's go and see. So we got our intersect function here. Actually, we do well. No, let's see. Intersecting for page. Yeah, what I was thinking is in here, if we really need to check all the quadrants. Because what I was thinking is if we contain the target rectangle in one of the quadrants, then we don't really need to check the other quadrants, actually. So maybe that will speed something up. Let's try it. So if quadrants top left, A, B, B, if this contains our target, well, we still want to check for intersections. Let's see, for this quadrant, even if it doesn't contain, because it can still, I mean, you can have entries inside that's gonna collide. So let's check that first, and then we say if we contain, then we actually don't need to check the other ones here. So, and there's also, I think there's another optimization you can do here where you do a broad search instead of a deep search. I'm doing a deep search right now because it was easier to think about like that. But you could do a actually you could do like a broad search instead of a broad first search instead of a depth first search, and I think that also maybe speeds up a bit, or it spreads spreads it out in some way. So but if this contains, then we actually don't need to check the other quadrants here. So we can actually do just return, I guess. Yeah. We can do it the same for the other ones. So let's say, because if the top left contains, so that means that the entire target is inside this quadrant. And all other rectangles that are like outside, they've already been checked outside this quadrant that are relevant. Then all entries in this quadrant are going to be contained within this quadrant. So it's enough if we check if it contains this, and we don't have to check for the other ones. So we can do this, and hopefully that maybe also speeds things up. I mean, we add some checks, but we also eliminate. Yeah, it doesn't seem to have that much of an impact. Not maybe not even anything. I thought I was gonna do something at least. Yeah, I don't know. Because you eliminate a bunch of checks. Yeah, I don't know. Yeah, maybe you could do this in a smarter way, but I was also thinking of doing like some sort of sweeping stuff, like sweeping along the, like, instead of doing like going through everybody and checking in the quad tree, you actually do like a sweeping thing along like the largest. So you divide basically the plane in, like, let's say you have 4 different rows. So you would sweep along this row, this red row here. So this part, you would sweep that and check all the collisions there. And then you would sweep this part, and then you would sweep this part, and then you would sweep this part. And maybe that would be a little bit faster, but I'm not sure. Yeah, anyway, that were all the optimizations that I had done from before. And yeah, I mean, it works good enough, I would say. In my game, I won't have that many objects, I don't think anyway, that's gonna need to check for these kind of collisions, I guess. But it's enough to, yeah, get me to play around with this type of quadry. And maybe, hopefully you've learned something here. And please follow along when I make my little game there with a taxi car and stuff, and see how that goes as well. So yeah, that's gonna be it for today. So thanks very much for watching. See you next time. Bye.